Well, hello again, class. Here we are, nearing the end of our academic school year, way past the end of our textbook, and we're just gonna wrap it up this week. This is the next to last lesson, section 3.8. The last lesson will be section 3.9, and this one should be pretty quick. It's about the derivatives of inverse trig. Now, I don't want you to memorize these things. They're ugly. I mean, look, I've got the table here for you. They're pretty ridiculous. The way I've laid them out is a little bit different than normal. I laid them out side by side so that way you can see the ones that are related to each other. Basically, the functions that are, what's the word I'm looking for, complementary to each other are side by side. So, sine and cosine are complementary functions. So sine inverse and cosine inverse also complementary. If you look at their derivatives, the only difference is, well, this minus sign. And same thing for tangent. Tangent and cotangent are complementary functions. If you look at their derivative, the only difference is this minus sign. And of course, secant and cosecant follow the same rule. So on this side I have the negative ones, and on this side I have the positive ones. So this table has a bunch of du dx's in it. And what that is that's the chain rule. So we're not saying that this is an x. You see, we're taking the derivative with respect to x. We're saying that u is any function in terms of x, which means the chain rule would have to be used. So this is the derivative of the outside, if you want to think of it like that. And here's the derivative of the quote-unquote inside. So for these notes, we are legitimately just going to be finding derivatives using these formulas. There's not anything to even understand. To be honest with you, you just use these things. Okie dokie smoky? All right, let's get right to it. This one simply says find the derivative of sine inverse of x squared. It should be written like this, sine inverse of x squared. So you're finding the derivative of that. So the chain rule is going to come into play here. So just to show you what the chain rule is doing, this thing is the argument, x squared. So its derivative, du dx, is just 2x. So our derivative is legitimately just going to be following the formula. 1 over square root of 1 minus argument squared times du dx. That's going to give us 2x on top, and on the bottom, square root of 1 minus x to the fourth. And that's it. There's nothing else to it. It's not magic. They're ugly formulas. Just use them. In the future, will you have to have them memorized? I'm sure some calculus teacher down the line, Ms. Blue Bomb, or for those of you that are maybe going to SCF next year, your calculus teachers are going to make you know these. For now, hey, I can't test you, right? So, I guess that's your gain. Silver lining and all that. Moving on. Derivative secant inverse. You can see that your argument is not just x. Your argument is 5x to the fourth. So we will say that u is 5x to the fourth. So du dx is just the derivative of that, 20x to the third. So you're just going to use the secant inverse derivative formula. 1 over the absolute value of the argument. And you'll see why here in a little bit. Well, maybe you won't, but you'll see what I'm going to do with it. Square root of argument squared minus 1, and then times du dx. All right, let's clean it up, because it does clean up a little bit, actually. So the 20x to the third belongs on top. Now let's talk about this. Absolute value 5 is 5. And x to the fourth, well, think about it. Plug in any number you can think of when you raise it to the fourth power. You're always going to get a positive result, which means the absolute value bars are not even serving a purpose here. So we can do that. And inside the square root bar, we just get 25x to the eighth minus 1. And we can do a little bit of simplification here. All three of these x's will be gone. It'll take away 3 of those 4. And of course, the 20 over 5 is going to reduce. End result of 4 over x root 25x to the eighth minus 1. that's it. Ta-da. Using the formulas. So let's, quote unquote, apply it, right? We have a modeling problem here. We have a particle moving along the x-axis. Its position at any time greater than 0 because, no such thing as negative time. Its position on the x-axis is going to be described as t, or tangent inverse of the square root of t. It says, what is the velocity of the particle when t is 16? Well, first of all, you would have to remember back to our lesson on, what's the word for that stuff? The physics stuff. No, not math. My wife is being a smart aleck across the table from me. Now I can't remember what it's called. Oh, kinematics. There it is. I remember. Anyway, we're going to have to remember from our kinematics lesson that velocity is the derivative of position. So we need to find the derivative with respect to x of tangent inverse of square root of t. So yeah, the chain rule is going to come into play again. This time, u, the argument, we're going to call it t to the 1/2. So its derivative is 1/2 t to the negative 1/2, which will clean up to 1/2 root t, if you want to call that cleaned up. So velocity with respect to time is, well, the derivative of tangent inverse is 1/1 plus argument squared times derivative of the argument. Hey, really cool thing's going to happen right here. This root and this square will cancel out as long as t isn't negative, right? You'd have to usually use absolute value of t there because you canceled an even radical with an even root, except remember t can't be negative anyway because negative time doesn't exist. So we can actually forget that rule for this example. It's going to give us 1 over this 2 I'm going to put on the outside just so I don't have to, well, it doesn't really matter. I could distribute it if I want to. Basically, I'm going to keep the 2. I'm going to keep a 1 plus t, and then I've got this root t at the end. So I didn't really do anything fancy. I just wrote the multiplication in a different order. Basically, because when I plug in 16, this was the easiest way to do it for me. Because, yeah, we need to know the velocity when t is 16. So v of 16 is 1 over 2 times 1 plus 16 times the square root of 16. 1 over 2 times 17 times 4. I'll save you the trouble of grabbing your calculator. It is 1 over 136. Incredibly slow velocity. And the last example in today's incredibly short notes is finding a tangent line. So we have to find the equation of a tangent line for the graph of y equals cotangent inverse of x at x equals -1. Well, y minus y1 equals m times x minus x1. Point slope formula is going to tell us that we need 3 things. We need m, which is slope, aka derivative. We need x1, which was given to us, and we need y1. It doesn't matter which one you find first. Let's go ahead and tackle the derivative of cotangent inverse, because that will give us our slope. M equals d dx of cotangent inverse of x. You go, okay, well, the derivative of this, if we look at the front, flip the paper over if you need to, is -1 over 1 plus argument, which happens to be x, squared. But that's it. So we can find our slope when x is -1. 1 plus -1 squared. Well, that's 1. That's 1 plus 1 on the bottom, so I have -1/2. All right, there we go. We know our slope is -1/2. Now let's try to figure out what our y1 is going to be. So y equals cotangent inverse of -1. So if you took the cotangent of both sides, you would get that the cotangent of y equals -1. And remembering that cotangent is Not opposite over adjacent like tangent. It's adjacent over opposite. Well, here's the thing. Just like tangent, cotangent is negative in 2 quadrants. Cotangent is going to be negative in quadrants 2 and quadrants 4. But what you have to remember here is that we're dealing with cotangent inverse. So you would have to remember all the way back to where cotangent inverse is allowed to exist. Now, this is a long time ago in our lessons, so I'm just going to go ahead and hit you with it. Cotangent inverse only exists between 0 and pi. It's like cosine, because that's where cosine would have existed. So what we do is we draw ourselves our quadrantals, and we remember that this quadrant is off limits. So the only place where cotangent could be negative would be in this quadrant. Well, this is positive 1, this is negative 1. That would make this a root 2. This reference angle is clearly a 45-degree angle, but because of where it is, that angle is going to be 135 degrees, also known as 3 pi over 4, because this is a pi over 4 right here. So our coordinate is negative 1 comma 3 pi over 4. All right, now we just fill out point slope form and we're finished. We get y minus y1 equals m times x minus negative 1, which is plus 1. And that's it. I'm hoping that you find the notes easy because we're legitimately just using formulas. But if you need anything from me, as usual, don't be afraid to reach out over Zoom. Don't be afraid to reach out over Zoom. I swear I'm smart. Anyway, I'll be talking to you guys soon enough.